In this topic review, we talk about discounted cash flow applications, so we're going to build on some of our present value or time value of money concepts and introduce a little more terminology here as well. First thing we want to introduce here is net present value. The idea of net present value is when we have a series of cash flows. So in its simplest application would be in like project finance or capital budgeting. And we will discuss this more in the corporate finance section, but we introduce it here in our quantitative methods. So if we have a project where we buy a machine today and then that machine is going to produce output which makes money for us over a number of periods, 2 years or 10 years or 20 years, then in order to decide whether that's a good deal to buy that machine, whether that would increase the value of our company and increase shareholder wealth, we need to take those future cash flows, calculate their present values, and compare that to the cost of the machine today. So that's what's going on here in this net present value calculation. This CF0, this cash flow zero, is at time zero, and that's usually our negative outlay, and then we have a series of positive cash flows. Now, it doesn't have to be like that, and we'll talk about deviations from that in a minute. But just to get this concept down, so we're taking the present values of all of these future positive cash flows, and this is going to be our negative outlay today. Well, if this is positive, then it sounds like a good idea to buy that machine. So that's why we're using this net present value calculation. Then it has other applications, but that's probably the simplest one to understand right off. So let's take a look at what some numbers look like, or what an example looks like using some simple numbers. We're going to use a 9% discount rate here. Our project, we have an initial outlay of $1,000 today, $100 today, and then we get back $25, $50, and $75. If we add those up, we see that those add up to $150. So there's some positive return here. We got to find out if that positive return is higher than 9% or not. So we take the initial outlay minus 100 and then take the present values of each of these three payments, 1 year, 2 years, and 3 years out, discounted at 9%, add them all up and find out our net present value is positive. Well, what that means is this would increase the value of the company, or at least the expected value of the company. These are projections of cash flows in the future. So a positive net present value would tell us, yes, this is a good project. We should undertake this project. It can also be interpreted as our expected change in wealth from undertaking this project. A related concept to this is the internal rate of return. So here, rather than putting in an interest rate and calculating the net present value, we're going to set the net present value to zero and say, what discount rate would we have to use on all of these future cash flows in order to have the present value of those cash flows just equal our initial outlay, so that the net present value is zero. Now, we can solve for this using our calculators, and there's detailed instructions in the Swayzer notes on this, but conceptually just take a look at what we're doing here. Now, we're going to find this internal rate of return, but first think of one thing. The net present value was positive. So what do we know about the discount rate we have to use to make that go to zero? Well, if it was positive, that means the present value of these future cash flows is greater than the initial outlay. In order to reduce the present value of those future cash inflows, we've got to discount them at a higher rate. So because the net present value was positive before, we know that our internal rate of return is going to be higher than the 9% discount rate that we used. And in fact, it is. It turns out if we calculate it, our internal rate of return is 19.4%. And this column here is just to verify that. So we take the present value of $25 discounted at 19.4%, the present value of the 50, the present value of the 75, we add them all up and we get zero, and that just verifies that this internal rate of return is 19.4%. Now, there are some possible problems. I talked about a simple project where we have an initial cash outflow that's negative and then positive cash inflows over a number of years. And we get a single solution for the internal rate of return. But if this project were more complex, if there was changes in the sign of the cash flows besides that initial one, then we could have more solutions to NPV equals 0. We call this the problem of multiple IRRs. So if we have a machine, say we buy the machine today, and then in the third year we have to totally rebuild it, so our cash flow is actually negative in the third year and then goes back to positive, we'd have two solutions, and we just can't decide between them. So we really can't use this solution technique when there's more than one change in the signs of the cash flows. Another problem we have with IRR is we can't really rank projects on it. Now, if we have a limited amount of money and we have to choose among 5 projects, all have positive net present values, well, it's clear we'd increase the expected value of the company by the greatest amount by choosing that group of projects we can afford to do that give us the greatest total net present value. And so we could rank the projects by their net present values. But ranking projects in terms of IRR can be different. One project may have a higher internal rate of return, but a lower net present value. And net present value is theoretically preferred because it's telling us the increase in the expected value of the firm. The IRR doesn't do that. So we can't rank projects by their IRRs. Now, we've introduced these concepts here, and we'll see more about them and use them when we get into the study session on corporate finance. Let's take a look. What's a holding period return? A holding period return is simply the increase, the percentage increase in the value of something from one time to the next. And that holding period could be 2 days or 2 months or 2 years or 20 years. That's why we call it just generally a holding period return. So let's take a look at this example. If we purchased an investment 9 months ago for $9, it's now valued at $10.20. So we've increased in value $1.20 from an initial investment of $9. And that's a return of 13.33%. So that's our 9-month holding period return. Now, sometimes securities and investments also have cash flows besides appreciation or depreciation in their price. So if we take a look at a stock that was purchased 1 year ago for $29, just paid a dividend of $1.30, and is valued at $30.50, our 1-year holding period return is going to include both the price appreciation and the dividend. So our ending value in the numerator now is the ending price plus the dividend. In the denominator, we've got our original amount of investment. So we still put ending value over beginning value, subtract 1, and get a 1-year holding period return for this stock of 9.66%. The next concept I want to introduce here is time-weighted returns. The idea here, we want to contrast time-weighted returns with money-weighted returns. The idea we're getting at is we have, say, a pension account that an investment manager is managing, active management of this account. Well, how do we measure his performance or her performance on this account? Well, one way would be to use an internal rate of return type measure, which we'll see in a second. That's a money-weighted rate of return that puts more weight on the returns on a period when there's more money in the account. But the idea for performance measurement is that the investment manager with a pension account isn't in charge of cash flows into and out of the account. The company may have to make required contributions into the account. The pension plan may have to pay out benefits. So these cash flows are not under the control of the manager, and we don't want them to enter into the calculation of the manager's performance. So when we have time-weighted returns, what we want to do is take a look at each period during which there's no cash in or out of the account. We just want to measure the performance over the period. The total return, including dividends, interest income, and based on those beginning and ending values. So for each period during which there aren't any significant cash flows in or out of the account, we calculate the holding period return. And these periods can be of any length, because what we're going to do is string them together, compound these returns out, and however many years that's for, we take that to the power 1 over the number of years minus 1, and we get the compound, the equivalent compound effective annual rate. On the money-weighted rate of returns, I said it's like an IRR measure. So here we're going to set the net present value to 0. We've got our cash flows here. Now, this is our initial amount in the account, and these can be, let's make that a plus now. So that's our initial amount in the account. And then if we add money to the account, these would be positive cash flows. If we had withdrawals, they would be negative. And then we'll treat this ending value as a withdrawal. So as if we took all that money out of the account at the end. Now in this case, we're going to solve for that discount rate that makes this net present value 0. But the periods must be equal length. So what we need is we need to use the shortest period during which there's no cash flows in or out of the account. The reason they need to be of equal length is because we're solving for a rate of return, and that rate's got to have a time dimension. So that's got to be a monthly discount rate, or an annual or semi-annual, or every 85 days, whatever fits the problem. So let's look at a problem here. We've got some simple numbers here to illustrate the difference between these two methods and also the calculations. If we invest $1,000 in an account at time 0 today, and after 1 year the value of that account is $1,200, well, we've had a 20% return over that first period. But at the end, the investor, the pension plan, adds $800 to the account. So now we start out with $2,000 at the beginning of the second period, and that grows to $2,200. So now we've got a 10% return over the second period. Well, let's look at these calculations here. We could just compound. During that first period, we had a 20% return. Second period, a 10% return. Compound that. Well, that was for 2 years, so we'll take the square root of that minus 1 and say the time-weighted rate of return here on an annual basis, 14.89% per year. Now, before we calculate the money-weighted rate of return, think a little bit about the intuition of this. We added $800 to the account at the end of the first year. So we've got more money in the account for the second year than the first year. Excuse me. 2,000 instead of 1,200 as a starting value. So the money-weighted rate of return is going to put more weight on the second year's return than on the first year's return. So the money-weighted rate of return should be what? More or less than the time-weighted rate of return? Well, it should be less because we're putting more weight on the second period in which returns were lower, 10% instead of 20%. And that's exactly what we find if we do the calculations. We solve for that internal rate of return, right? $1,000 into the account at the beginning, $1,000 in after 1 year. Ending value must have the opposite sign, in this case 2,200, as a positive number. We solve for the internal rate of return and get 13.623%. So, which one should the manager be measured with? Well, we say the time-weighted rate of return because he didn't make any decisions about adding money to the account for that second year. We'll just hold the manager responsible for the returns during the period based on the money he starts the period with. So that's a money-weighted versus a time-weighted rate of return. And with your cash flow keys, we put in the first cash flow, minus 100, then minus 800 is cash flow 1, 2200 cash flow 2, solve for the IRR that makes the net present value 0, and find out that that's 13.623% for our money-weighted rate of return. Okay, let's define 4 more things here. Well, I guess 3 more because we've had the holding period yield already. So what's the bank discount yield? Well, especially for money market securities that trade at a discount from face value, they don't pay explicit interest, like a treasury bill. You buy it at one price, it matures at $1,000, and that difference is your implicit interest and your return. But it's also the discount percentage from face value. So the bank discount yield is not really a yield, it's an annualized discount. And we're going to annualize this discount by multiplying by 360 over the number of days to maturity on our treasury bill or other money market discount instrument. Our holding period yield, we already know, ending value over beginning value minus 1. Our effective annual yield, well, that holding period yield can be for any period of days, depending on the security we're looking at. To get an effective annual yield, we take that to the power 365 over the number of days minus 1. So just like compounding out to an effective annual yield. Our money market yield also starts with our holding period yield, but instead of compounding, we annualize it using a simple formula, 360 over the days to maturity. Note that that's the same thing we did with the discount, but notice the difference here. With the bank discount yield, we annualized a discount from face value. With the money market yield, we annualized the holding period yield, which is going to be higher than the discount amount. And we'll see that in our calculations here. So here's our example of these calculations. Say we've got a 90-day T-bill. It's priced at $9.80. It's going to pay $1,000 at maturity 90 days from now. First calculation, what's the bank discount yield? Well, $20 discount, $1,000 face value, that's a 2% discount. But it's a 90-day T-bill, so we've got to annualize that by multiplying by 360 over 90, which is 4. So we end up with an 8% annual discount yield. Now, if you're looking at various treasury bills, and you've got some that mature in 73 days and some that mature in 120 or 170 days, we want to use this annualized measure because then we can better compare the yields on these, at least in terms of their discount, on an annualized basis. Otherwise, it'd be very hard to compare them. The holding period yield, we get $1,000 at maturity. We're paying $9.80, so our holding period return is 2.04%. A little bit bigger than the discount, right? Because we could also write this yield, this holding period yield, as our gain, $20, over $9.80. So now you can see that that's always going to be larger than the discount. The discount is based on a percentage of face value, the holding period yield based on a percentage of our initial investment or purchase price. 2 more of these to go. The equivalent annual yield or effective annual yield. Take that 1 plus that holding period yield, 2.04%. Compound it out for just over 4 periods, 365-day actual year, over 90 days, the maturity of the treasury bill. So our holding period yield is for 90 days, minus 1. And we see our effective annual yield, and that's really telling us if we were to reinvest at that rate just over 4 times, we'd earn 8.53%. based on a 365-day year. Our money market yield is also keyed off the holding period yield, remember, but the annualization is like with a bank discount yield. simply multiply times 360 over 90 and get a money market yield of 8.16%. So of all these, which is the largest? Well, the effective annual yield is going to be the largest because it reflects compounding. The money market yield is our next largest. It doesn't affect compounding, doesn't reflect compounding, but it is an actual yield. Our bank discount yield doesn't reflect any compounding and is also a discount from face value, which is going to be less than our actual yield. Excuse me. The last part here, bond equivalent yield. We're going to define this here as 2 times the effective semi-annual yield. So what we want is the 6-month compound rate. So look at this first example here. Annual effective yield is 8%. Calculate the BEY. Well, we've got the annual effective yield. What we need is the semi-annual effective yield. So we want to know what compound rate would we have to earn every 6 months to end up with an 8% effective return. Well, if we take 1 plus that annual effective return, take the square root minus 1, we'll see that if we earn 3.92% every 6 months, compound that twice a year, that would end up to be an effective annual return of 8%. So now to get the bond equivalent yield, we're just going to double that. Perhaps it would help a little if I explain that bonds mostly pay semi-annually. So if you say you've got a 5% bond, it's really paying you 2.5% every 6 months. So 2.5% is your, every 6 months is your effective rate on a 6-month basis. 5% is 2 times that. Of course, our effective annual return with semi-annual compounding is going to be a little higher than that. In this case, we know our effective rate is 8%, but our bond equivalent yield, 7.84%. Now, one last application of this bond equivalent yield, sometimes we'll have securities that pay monthly. Mortgage-backed securities many times have a monthly yield. So say we said our monthly effective yield is 0.75%, 0.75%. Calculate the BEY. Well, again, as soon as we know we want the bond equivalent yield, we've got to figure out what's our effective semi-annual yield. Well, in this case, we have a monthly yield. We need to compound that monthly yield for 6 months. If we earn 0.75% per month, compounded for 6 months, that would come out to 4.59%. To get the bond equivalent yield, just double that. So 9.18%. Okay, let's end up this review with a problem, just to make sure you remember these. We've got a 90-day T-bill. It's purchased for $997.40, so I guess we're getting a little more realistic in terms of yield here. What are the discount yield? What's the holding period yield? And what's the money market yield and the effective yield? Well, the discount is just the percentage discount from face value, and that's around 0.25% here. Here's our discount. What is that? $2.60 over 1,000. So that's 0.26%, but it's a 90-day bill. We have to annualize this discount yield and come up with a discount yield of 1.04%. Now, as far as our holding period yield, we're going to invest $997.40 and we're going to earn $2.60 over 90 days. So we can calculate it this way, but this is also equal to $2.60. I think that's right. Yeah, $2.60 over $997.40. Not the best writing in the world, but you get the idea. So that's our 90-day holding period yield, the percentage increase from $997.40 to 1,000. How about our money market yield? Well, we just need to annualize on a simple basis that holding period yield, 90 days versus a 360-day yield for this year for this calculation gives us 1.2607%, our holding period yield, times 4. So our money market yield is 1.0428%. Our effective annual yield, well, that's going to reflect compounding, so it's going to be a little bit higher. Let's see how much higher. We can take ending value over beginning. Now remember, what's in that parentheses right there is also 1 plus the holding period return or yield. Take it to the power, 365 over 90, subtract 1, and find out our annual effective yield is in fact a little bit higher, 1.0614%. So again, everything lines up. Now, you also may be required to switch from one of these to the other just to demonstrate your understanding of it. And my suggestion there is that you always key off the holding period yield. If I have the holding period yield, I can certainly make this calculation. And if I have the holding period yield, I can certainly make that calculation. Or if I have the effective annual yield, I can just take 1 plus that and take the inverse of that power, right? If I take 1.010614, 1 plus that effective annual yield, and take it to the power 90 over 365 minus 1, I'll get right back to my holding period yield from this effective annual yield. So I can go backwards to this, and then from my holding period yield, I can get back to the discount yield. I can get back to the money market yield or the effective annual yield.